All right, class, today we're doing section 8.3, part 1, and there'll probably be 2 parts to this because this one's kind of a long one, so this will be part A on YouTube. We got to get through 4 tests: integral test, P-series, comparison test, and limit comparison test. More tests, that's what we're headed to. So let's just take a look. I want to just talk about a few like kind of reminders or things, and then we'll head to 8.3. First of all, remember we've got our special series so far, our tests. We've got our harmonic, we've got geometric. Our first kind of official test is the test for divergence. And then we also have the, can we see it at the bottom? Yeah. We also now have the telescoping sum. Okay. And make sure, remember, I didn't correct this until B, so I'll try to send an email out. Remember, these are R's. Make sure, can we see everything on there? Yeah, I think we can see everything. Okay, and we'll keep referencing this, so don't panic. They kind of all come together. I don't know if that's good or bad. We kind of keep folding things in, but we'll still see these things a lot. So that's why I wanted to mention that. The other thing I wanted to mention is, and this is kind of the reason we do the telescoping one, only 2 tests where if the series converges, we can actually find the sum. Okay, geometric, because we know that the sum then is a over 1 minus r. And then telescoping, when we go find that limit and we come up with a numerical answer, that is the sum. I wanted to make sure that I said that. When we do the telescoping and we do the limit, that answer is the sum. But these are the only 2 tests. From now on, our answers, and that's why I wanted to make sure I said the telescoping, the answer is the sum. But for these other tests, that is not the case. The number will tell us if it converges or diverges, but it will not be the sum. Telescoping is very isolated. It doesn't come up a whole lot, but because it's one where you can actually find the sum, I thought it was important to go over it. Geometric comes up a lot more. And again, but that's the other one where you can find the sum. But telescoping, it doesn't come up very much. You have to be able to factor the bottom and get to, specific things, if it's irrational, if it's fractions. But the nice thing about the telescoping, if you can get it to fit a telescoping, you can actually find the sum. The rest of these, we'll know if it converges or diverges. The rest of these tests will tell us if it converges or diverges, but we will not know what it converges to. So that's kind of the interesting thing about that telescoping. That number we come up is the actual sum. Okay, and then one other thing I wanted to cover is, you don't have to write this down, okay? But I wanted to remind you, especially if you had the Calc 1 with me, we spent at least one day, maybe even next year will it's fun too, but remember when we had these rational fractions and we factored them and then we canceled them and we got a whole bunch of things. I didn't even write on here. I wrote whole, vertical asymptote, horizontal asymptote. I think we also did x-intercept and y-intercept. I think those were the other 2 things we did. And remember, the whole is what makes what got canceled. I always say crossed out, but I prefer canceled. What makes that 0? Vertical asymptote is what makes the bottom 0. But I want to focus on the horizontal asymptote. The horizontal asymptote, or better yet, end behavior, correlates to if something converges or diverges. Okay? If the highest, and we wrote this, if the highest exponents are the same, the horizontal asymptote or the end behavior is y equals the lead coefficients. Okay? If the bottom exponent would be bigger than the top, then it's automatically y equals 0. Okay? And if the top is actually bigger, then it's actually not a horizontal asymptote, it is a slant asymptote. Okay, so now why are we going over mainly the horizontal asymptote? Let's take a look. One last thing here. The reason that is the case, is because of either L'Hopital's rule, okay, or Remember we said we divide everything by whatever's on the bottom, the highest exponent on the bottom. If we divide everything by x squared, okay, and then we simplify, we get this guy. And if we're taking the limit, right, we plug in bigger numbers, this heads to 0, this heads to 0, all these head to 0, except these here, which this number then, so the limit is 1, which is also the lead coefficients. So if I don't want to even use L'Hopital's rule, if I don't want to divide everything by x squared, the highest exponent in the denominator, I can just memorize this. All right, the limit, if the highest exponents are the same, will be the division of the lead coefficients. The limit, if the bottom exponent is bigger, will be 0. And the limit, if the top is bigger, the limit then would actually be infinity. Okay, so it's kind of like a shortcut. So I'll talk about, as I go through it, I might use the shortcut, but the shortcut is you're basically memorizing what dividing by x squared would create, or you're kind of memorizing what L'Hopital's rule would give you. Just a kind of a shortcut if you want to use it, and I'll talk about it every time it pops up. But I thought it was also kind of cool how to tie in horizontal asymptotes and limits. Okay. All right. We got enough to do. If you don't like that, don't panic. Like I said, I'll kind of mention it when it comes up. We'll figure it out. Okay. Did I show this already? 4 more tests. We got the integral test, the p-series comparison test, and limit comparison test, if we didn't have enough. And then 8.4 is even more tests. Okay, but we'll get through it. Don't panic. Okay, so let's take a look at one at a time. We're going to do the integral test. Okay, so if we have the sum of some function, okay, instead what the integral test says is we can actually change it to an integral. We're going to actually change this. This function is this guy. We're going to just put it in terms of x. Okay. Notice because we're going to infinity, so a to infinity, because we're going to infinity, that's those improper integrals. So we'll practice how to do those again. If the integral converges, the series converges. If the integral diverges, the series diverges. Okay. All right. Remember, the answer that I get for this integral is not necessarily what, it is not what this converges to, okay? It just tells me that it does converge, okay? This integral is gonna give me the sum of like areas and different things. This is just gonna be the sum of the numbers, but it will tell me if it converges or diverges. Let me see if I have a picture. There's kind of like a proof here, okay? So we're doing the sum of the integrals, all right? And here's my actual function, okay? So it will at least tell us whether it converges or diverges, but it does not converge to this numerical value, okay? All right, if the integral converges, the series converges. If the integral diverges, the series diverges. All right, so let's see, where's all this stuff? And if you need more time to write that down, okay. All right, so let's try a few. Okay. I got all these pages here. I'm trying to have things already written out, but everything's kind of chaotic. Okay, here we go. Use the integral test to determine whether the series is convergent or divergent, okay, or whether it converges or diverges. Notice it does not say if it converges, find the sum, because this test will not give us what it actually converges to, okay? All right, so let's take a look at our summation here. N equals 1 to infinity, and we're doing 3 over n to the 5th, okay? All right. So what the integral test says is let's change this to an integral, okay? So we're going to change this to, make sure you guys can see, okay, 1 to infinity, okay? and we're going to do 3 over, and you can do n still if you want. If you want to change it to an x to kind of officially say, hey, we're changing this type, we're literally changing the type of problem it is, you can. If you just like x's, that's okay too. Okay. All right, so now do we remember if this goes to infinity, we actually did the limit as c goes to infinity, and then we said we're going from 1 to c, 3 over x to the 5th dx. Okay. What else? Okay, so now I think we need to take the integral of this, so we need to move that up, make it a negative exponent, the limit. So now let's actually take the integral. We won't worry about that part for a while. We're going to write this as 3x to the negative 5 dx. Okay. Okay, so now we're going to actually add 1, divide by the new. Take your time, add 1, divide by the new. So that gives us what? Negative 4, and then 3 divided by negative 4. And we're going from 1 to c. Add 1, divide by the new. So remember, we're taking the limit as c approaches infinity. We'll plug in the c. So we got negative 3/4. Maybe we'll move this to the bottom. I like to always move that back to the bottom. Remember, we can actually rewrite this, right? This can come to the bottom, to the 4th. Okay. So let's put, so let's actually plug the c in there then, right? So it'll be c to the 4th. Okay, now just be careful. It's minus, and then a negative 3/4. And then we'll plug the 1 in, 1 to the 4th. Okay. All right, so this 1 to the 4th is still 1. This turns out to be what? Plus 3/4. And then we still have to worry about this guy. The limit as c goes to infinity of negative 3 for c to the 4th. Okay, so how are we doing? Okay, we can see. All right, so what happens is we plug bigger and bigger and bigger numbers in to the bottom, to the denominator. If bigger numbers are going into the denominator, this is headed towards 0. So this guy is 0, and this is 3/4. Okay, so if, what was it say? If the integral converges, okay, if the integral converges, then the series converges. Okay, so here, this 3/4 means the interval, or what am I saying? The integral converges. Therefore, do we know this little triangle means therefore the series converges. Okay, if the integral converges, then you could put then or therefore the series converges. If, oh, I know, let me sneak one more thing up. On the homework, it says that if the integral is finite, okay, which is maybe a little bit better than saying that the integral converges. It's iffy either way, but so our book, and I like it too, I have to be honest, it says if the integral is finite, then, or therefore, the series converges. If, yeah, we could put if there. If integral is finite, instead of converges, then series converges. Okay. All right. And so we could actually, should we go back here? If the integral is finite, then the series converges. If the integral is infinite, instead of diverges, then the series diverges. Okay, so they use that word for integral, which does kind of make more sense. Okay, all right, let's try another one. Does it converge to 3/4? Is the sum of the series 3/4? Absolutely not. Okay, that only works for telescoping or the geometric, we plug it into that little formula. But at least it tells us that it does converge. Okay. All right, let's try another one. We did all that. All right, how are we doing, guys? Okay, let's take a look at, oh gosh, make sure you guys can see. Okay. The summation from 1 to infinity, and again, our book mentions, like if we start at 4, we start at 3, it doesn't really matter. Okay, because we're going to infinity, it doesn't overall really matter where we start. Okay, 2 over the cube root of n. Okay, now remember, we're going to use the directions specifically say use the integral test to see if it converges or diverges. So the integral test says literally change this to an integral. So we're going to go from 1 to infinity of 2 over, and again, you can use x, you can use n, whatever you like. If we kind of change it to x, it's kind of reiterating that we are literally changing it from a summation to an integral, but variable at the end of the day doesn't matter. What else? Okay, because this is an improper integral, we actually do the limit as c goes to infinity of 1 to c. And then let's rewrite this. We're going to rewrite this as 2 and then x to the negative 1/3. Okay, bring it up and change it to an exponent. Okay, so now we can actually take the integral, add 1, divide by the new. So if we add 1, we get 2/3. Okay, 2 divided by 2/3 or multiplied by the reciprocal. That turns out kind of nice, right? That cancels, so we get 3x to the 2/3, and we're going from 1 to c. Okay. All right, so now let's take the limit. Make sure you guys can see the limit as c goes to infinity of, we'll plug in the c, so 3x to the 2/3 minus 3 and then 1 to the 2/3. Okay, so 1 to the 2/3 is still 1 times 3, so this part is negative 3. What happens here? Okay, and it's up to you if you want to take a look at it. You can write it as what? It's the square root, or no, I'm sorry, it's a cube root, right, of x squared. However, it is easier to see. But when you put it in bigger numbers, you are going to square it, and then you're going to take the cube root. But the bigger the number that goes in there, this is just going to get bigger and bigger and bigger. Okay, so this is infinity. Okay, this limit is headed to infinity. So we would say if the integral is infinite, right, because this limit is headed to infinity, so let's write if integral is infinite, therefore, or then the series diverges. Okay. If the integral is infinite, then the series diverges. All right, let's try one more, and then we're good. We'll move on to more tests. All right, so let's try this. Let's try this one. Summation n equals 1 to infinity, and we have 1 over the square root of n plus 4. Okay. All right, so specifically we're going to use, and we could write that here, we are going to use the integral test. I'm going to use the integral test. Okay. And right now we're just getting familiar with the test. The second part of 8.3, we're going to kind of like look at problems and then kind of start to decide what test we should use. So today is just, here's the test, can you use it? Okay, so kind of going to try to take it in stages. Okay, so integral test says I'm going to actually change this to an integral from 1 to infinity. We can actually, do we want to write the, well, let's at least change this to, we'll do x plus 4 to the 1/2. If we want to make it negative, well, we probably should have, but that's okay, dx. What else? Okay, because it is going to infinity, we're going to do the limit as c goes to infinity from then technically 1 to c. And yeah, let's write this. Let's go ahead and even bring this up. So we'll do x plus 4 to the negative 1/2 dx. Okay. What's our issue here, though? We've got a quantity. So if we have a quantity, we have to do u substitution. So u is going to equal x plus 4. I think we are okay, though, because this turns to what? Du, and then this simply turns to dx. So we don't get any extra pieces, and that's okay because we don't really have anything extra floating around. We don't even get a number because the derivative goes to 1, which is great. So we're still doing the limit as c goes to infinity from 1 to c, but now we can officially make this one group u to the negative 1/2, and then dx goes to du. Okay. All right, now we can actually take the integral, add 1, divide by the new, so we'll add 1. That takes us to what? U to the 1/2. And then divide by 1/2 or multiply by the reciprocal. So that would be 2. Okay, we're going from 1 to c. All right, so we got the limit as c goes to infinity. We'll plug in the c, so we've got 2. We can do this as the square root of c if we want, minus 2 and the square root of... Oh, no, what do we have to do? We technically have to change it back, really. Get out of there. Let's, all right, hang on. We got to change it back, right? So we got the limit as c goes to infinity of 2, and we got to change this back to x plus 4. That looks better. And then we're going from 1 to c. All right. So now we can plug this in. Remember, that was u, and these guys technically, even though there's not much to it, technically those guys are x's. So let's put this back. Now everything looks beautiful. Okay. All right. Limit as c approaches infinity, 2, and then c plus 4 minus 2 square root of 1 plus 4. Okay. And this we can simplify for sure, but main thing is what's happening here. As this gets bigger and bigger, this guy's just going to get bigger and bigger. I'm going to add 4, take the square root, but I can always find a bigger value. So this guy goes to infinity if the limit is infinite. If integral is infinite, then, or therefore, series diverges. Okay. All right, so we'll talk every once in a while about the integral test. It's kind of isolated as well. There's some other tests that kind of come up, but it's always good to, and it's kind of nice, right? We spent how many chapters on integrals? We might as well use it a little bit more. Okay, we did that, we did that. Okay, it looks like, actually in my notes, it looks like they may say if the integral is not finite. So something like that might come up on WebAssign. Infinite, same thing as not finite. Leave it to them to always change it just a little bit. Okay, all right, now that's the integral test. Okay, add it to our list of tests, right? Okay, now let's take a look at the P series. Cover up part of this for 1 second. How are we doing at time? Okay. Right, we could talk math all day long. Okay, so now here's another one, a P series. A P series is a summation if you have 1 over n to some exponent. Okay, if you have n to some exponent, if the exponent is greater than 1, it converges, and if it's less than or equal to 1, it diverges. Okay, so that's not too bad. The P series is actually kind of nice. If it's greater than 1, it converges. Remember, we won't know what it converges to, but we will know that it converges. And if P is less than or equal to 1, it diverges. Okay, I want to take a look at this one thing. We're going to come back to the P series. Oh, dear. Okay. So I want to take a look at this guy for a second. N equals 1 to infinity, 1 over n. okay? We actually have written this before, okay? This is a harmonic. And this is where it kind of all starts to blend together. And it doesn't always do this, so don't panic too much. But I also kind of want to show you some different things that happen. This is harmonic. Okay, harmonic, always, it's 1 over n. 1 over n is harmonic. It always diverges. Okay. We can also think of this as a p-series. Okay. A harmonic is just a special p-series. It's one that comes up quite a bit. But a harmonic is just a special p-series, okay? P-series, you can have any exponent you want up here. For harmonic, it's always 1, okay? But notice that p is equal to 1. So for a p-series, if p is less than or equal to 1, which for us, p is 1, okay, then this says it diverges. Okay, so just another way. We can call this one harmonic. We can also call it p-series. Okay? And I want to take a look at it doing the integral test. Integral test. Okay, so let's change this to an integral. 1 to infinity of 1 over x dx. Okay, the limit as c approaches infinity from 1 to c. We could leave this as 1 over x dx, because now when we actually take the integral, what's the integral of this guy? The integral of this guy is ln x, right? So the limit as c approaches infinity of ln x, we're going from 1 to c. Slide it up just a little. So we got the limit as c approaches infinity of ln c minus ln of 1. Okay, this guy goes to 0, right? But the main thing is, as this number gets bigger and bigger, a natural log makes it slow down. It doesn't get big quick, but it will continue to get bigger. If we need it, we can make it bigger and bigger and bigger. So if the limit is not finite, right? If it equals infinity, all right? If integral is not finite, series diverges. Okay. So just like I said, things start to overlap a little. Don't completely panic. It doesn't happen a lot, but I wanted to show you this harmonic series, literally harmonic always diverges. This is also a p-series, which it follows the rule it diverges, and we can even show it using the integral test that it diverges. Okay, so just different ways to kind of look at the same problem. That'll come up a little bit, so don't panic, but most of the time there's kind of usually one way to do it. Okay, let's take a look at the comparison test. Okay, there's a lot here. Okay, the comparison test, this is your given series. Okay, this is given. Okay, what you're going to do is you're going to come up with a series on your own. Okay, I call this the benchmark. This is the benchmark. Let's see, what else did I write? You choose. I think I write, what's the best way to write this? Yeah, you choose. Okay. You choose. Okay. All right, and these just both have to be series with positive terms, which most of the time they are. Okay. If the one that you choose is convergent, okay, if you choose this one and you know that it converges, okay, and these are always smaller than these, then this has to converge. Okay, so if you can prove that this converges, and these are always smaller, then they have to converge too. Okay, the opposite. If this guy, if you know for sure that this diverges, the one you choose, okay, the one you choose diverges, and you know that these are always bigger than these guys. So if this diverges and the original problem is even bigger, then it has to diverge too. Then your original has to diverge. Okay, so if this converges and this is smaller, then this has to converge. If this diverges and this is even bigger, then this has to diverge. Okay, B sub n is a benchmark, it's what we choose. Okay, most of the time we're going to choose a P series or even the harmonic. That's really easy. Harmonic always diverges. Okay, so you can use that as a benchmark. Okay, or a geometric series. Okay, those two are the kind of the nice ones to use for a benchmark. All right, we're going to go through examples, but that'll kind of give you a heads up. Okay. All right, let's take a look at one. So we're going to use the comparison test. Okay, let's actually stop there. Let's stop there, and then we'll actually go through examples on part B. Okay, because we're at about 30 minutes. So actually, let me put this back up so you can copy this if you want. Let it sink in, and then B, we'll try some examples.